Some chapter 20 things that you should know cold, some basic knowledge. So let's start out with the concepts. So first off, dealing with current. That current is just a flow of charge. So I can either have negative charge flow or positive charge flow. Just recognize that in almost anything that you are going to deal with, current is caused by negative charge flow. It's by the electrons that are flowing. There are exceptions, and in high energy physics, you could take a hydrogen atom, strip the electrons from the protons, and now you have electrons and protons that you can shoot around. For my dissertation, we were dealing with protons that were put up near speed of light and shot. There was definitely a current flowing there. But this does bring in the idea, the fact that there are two types of current. There's the traditional current, otherwise known as current. And then there's electron current, which textbooks sometimes do. And the reason why there's a distinction here is that Benjamin Franklin was originally picturing a fluid that was flowing, and so he established current flowing from high to low potential, and then later we realized it was the electrons moving that were going in the opposite direction. So traditional current or current travels opposite direction of the actual electron flow. Resistivity and conductivity are two concepts. These are material dependent. So if you're asked to find resistivity, you can find it experimentally, you can look it up, or you can calculate it based on the information given, but these are dependent upon the material. Resistivity is a material dependent quantity that depends upon how hard it is for charges to flow, and conductivity is the reciprocal of that, and this is a measure of how easy it is for charges to flow. Then we have Kirchhoff's rules. There are two rules involved here. One, that at any point in a circuit, the current flowing in equals the current flowing out. This is known as the junction rule or the current rule. Do note that this does bring up a potential problem that does get resolved later of what about a capacitor? Current flows onto a capacitor, then there's a gap, and then current flows off of a capacitor. And so we need to be careful about that. It does not affect anything particularly greatly, and that issue does get resolved later. And the other one is that if I take any point in a circuit and I do a loop around it and I end up back where I started, that my voltage is zero between any point in itself, regardless of the path. This is known as the voltage rule or the loop rule. And that is it for the concepts. Those are all the symbols. Let's take them step by step. So we have current, which is symbolized by the letter I. I think this comes very simply from the fact that current flows in a line, and that's just kind of looks like a line. I suspect that's where it comes from, as opposed to from the Latin or the Greek, but I could be off on that. But anyway, I is used for current. Later on, when we get to AC current, we will start using the lowercase I to represent instantaneous current and capital I to represent the maximum current. Capital R for resistance. You can probably figure out where that one comes from. Rho for resistivity. That is a rho, R-H-O. And then conductivity, that is a sigma. And we primarily deal with resistivity, but there are some problems that have conductivity come into it. And then we have the symbols used for the units. We have capital A for ampere, and this is a capital omega. The lowercase omega kind of looks like a W. That's the lowercase omega. We use that for angular frequency and angular speed. This is the capital omega and is for ohm. The ampere was named after ampere, and I'm sure you can pronounce it better than I can. And this was named after ohm. The symbols, let's do them step by step. This is part 2 of the symbols. When we draw circuits, we have certain symbols that we will use. This is the symbol for a resistor. This represents a wire that is bound very tightly together. So that is the resistor. We have the battery. We have a negative side and a positive side. The positive side is longer. If you think about a plus sign, requires twice as much ink as a minus sign. That's the positive side. That's the negative side. Technically, a battery has to have at least 2 of these units right here. These units are known as power cells. However, when I do it, I will also represent this as a battery. This has bugged a couple of students in the past, not many, but Just recognize that the purists will say that this is not a battery, this is a power cell. It functions the same from my point of view. Capacitor, this is representative of the fact that of the parallel plate. This is a non-polarized capacitor. This is what I expect you to know cold. There are other type capacitors where one side might be bent. There are a couple of different ways that you can represent polarized capacitors. And a polarized capacitor is just that it matters in which orientation you put it into a circuit, but we don't care about that. So that's the capacitor. Units. The unit, the SI unit for current is the ampere, and that's just the coulomb per second. The SI unit for resistance is the ohm. There are no new constants for this particular chapter. There are no new definitions for this chapter that haven't already been covered here. Formulas. Let's do it step by step. Current is the amount of charge passing by a particular point at in a certain amount of time. And this is why if you look at the units, this is units of charge as coulombs per second, and that is equal to an ampere. We also have Ohm's law, that if we're dealing with a particular resistance, if I know the potential drop across a resistor, then I divide by the resistance, I can find the current. Or if I know the current and the resistance, I can calculate the potential drop. There will be labs involved in this. Well, it depends on how much time we have. Or if you're just trying to calculate resistance from the material length and cross-sectional area. So resistance is resistivity times the length of the wire divided by the area. We definitely will be doing a lab on this one. This cross-sectional area, if I have a wire that is running along like this, the cross-sectional area is the area here. So if I cut it, what is the area? Length, that would be length. And then that is material specific quantity, known as the resistivity. We get into power. I don't think I have a video on power. You can read about that in the textbook, but this is just P equals IV. This is the rate at which energy is used. If you're dealing with a power supply, then you have the voltage between the two ends of the power supply times the current flowing out of it, and this tells you how much energy is being produced. If we're talking about a resistor, so all three of these could be used in terms of a resistor, this would be the power loss in a resistor, because the resistor basically will heat up. It's causing particles not to flow as smoothly as possible. And so therefore, this is the power, this is the rate at which energy is being drained if it's a resistor. And if it's a power supply, then those two don't necessarily apply. This is the rate of energy being produced by a power supply. And that is the knowledge that I would hope that you would know cold.